And yeah, let us not delay. Let's begin. So I can always, yeah, always hide it. Okay, so basically we were trying to compare. We were comparing two different versions of Riemann integration. Okay, I've shared my screen. Okay, and from here we will come to some interesting questions. So compare two different I should say two different approaches, right? Two different approaches to Riemann integration. Okay. So I will summarize things a little bit, but I'll first say just this. This is what in general this is what we were trying to do. But then what were the two different approaches? Okay. Well, it was based on the type of partitions we use, right? So we had this regular partitions, which was the approach that I had taken. We kind of came to this while looking at how to make sense of area of sets, how to make sense of area under a graph of function and things like that. So we were looking at this regular partitions. And then, so this is very uncommon. As far as I've seen in books, it's very uncommon approach. Okay, I will go a little bit in more detail in that as much as you guys want me. Okay, so we'll see, but the on this level that we had this regular partitions and then we had this general partitions, which is much more orthodox. You open any book like Spivak, Partition, Rudin, they look at general partitions. Okay, they don't put a restriction on what kind of partitions you have to use. Okay, so these are the two theories, and then we want to understand if these two are the same or different. Okay. Now, obviously, immediately to all of you, maybe it doesn't make sense by what does it mean that these are same or different? Okay, these are obviously different maybe. But in the end, do they capture the same functions? Is something Riemann integrable with respect to this and not Riemann integrable with respect to this? Is it possible? I'll ask those questions specifically now and reverse question and so on. And if both the things give rise to the same integrable functions, then formally there is no difference. Still one may be more convenient than the other and so on, but formally there will be no difference. So that's what I mean, are they the same? So are these, well, they're not same, maybe I should say, are these equivalent? It's a better way. So again, let's make the setup. Should I once again go over the setup? So let me go over it, okay? And please ask me, please stop me and ask me questions. If I'm going too fast or too slow, you should tell me, okay? So I'll go first with the regular partitions approach. And I mean, both are just similar. In the end, there is a slight difference, but yeah. So we begin with a function. So again, this is not, I'm not writing continuous, it's not continuous. It's just a function from A to B to R. Let's just take 0, 1 to R. Now remember, it is bounded. Okay, we are assuming that for now. Yeah, we will have to assume that. Yeah, otherwise it goes into indefinite integrals. But yeah, right now it is bounded. So I'm not drawing the graph now, just saying that because we've seen this. So we say that f is I'll just say integrable because this is the only kind of integration we are doing. We say f is integrable. Okay. So I'm describing this side. Okay. F is integrable if for any delta for any, let's say for any epsilon greater than 0, basically what is the sense of being integrable? We want to basically say that the upper sum and lower sum essentially become the same eventually. They become the same eventually, which means that the difference between upper sum and lower sum can be made as small as you want by taking small enough partition. Okay, so I just formalize that. For any epsilon greater than 0, there exists a delta, okay, such that the upper sum for this delta partition. Now, delta partition, do all of you understand what is delta partition? This delta partition just means, yeah, it just means 0, delta, then you have delta, 2 delta, and so on till in the end. I mean, if you're going to cross 1, then you just do 1. If for some n, if after that, if n plus 1 delta is more than 1, then you just do n delta comma 1. Okay, so it's clear that's what delta partition means. And this is a regular partition. It is regular because all the sizes are same. Okay, you guys can tell me because this is a repetition I'm doing more or less. Though every time there's something, but okay, so you guys can also tell me. That will be good. In different words you'll be saying, and so it's good for all of us. You also and whoever is saying. So I'm not writing this. I'm erasing this delta thing. This is a very nice way to do things. So this upper sum p delta of obviously f, but let's write f. Okay, otherwise it looks very strange. Minus the lower sum. Do I need to say what is upper sum and lower sum? Okay, all right. If anybody wants me to say it, I'll say it. Okay, but fine. So this is upper sum minus lower sum is less than delta. Okay, so can we put this in a different way? Just this thing, is it possible to put this in a different way? Yeah, well, another way to put it is limit delta going to 0, right? This upper sum minus lower sum, or take that on the other side also. This thing, this limit is equal to 0. These are the same things. Okay, sorry, so this is epsilon, right? Nobody stopped me there. This is epsilon. I want to make the difference less than epsilon. Okay, so here you see, here the partitions are tagged by a very good set, that is delta, which is a real number. So it makes sense to say, okay, delta goes to 0. Okay, so as you take, so if you go over all the partitions, then that you can make the difference as small as you want. But in this way, I mean, it's very obvious that as delta becomes smaller, the difference becomes smaller. And so if there is any hope for this to go to 0, it has to be when delta goes to 0. Okay, so that's the thing. Okay, but here note that here we are only having access to regular partitions. We are not using other kinds of partitions. Okay, we are not using other kinds of partitions. All your partitions that you use here are going to be regular. And I'm putting it in this way, so you must understand the power of both. Then you'll be able to tell which one is more powerful or not a priori, and then are the equal in the end, and so on. Okay. Using only the regular partitions, you have to make the difference smaller and smaller. Using only regular partitions. Okay. So now that I have defined this theory from the regular partition perspective, I want someone to tell me the analogous thing for general partitions. So obviously, I mean, till here it's going to be the same, but maybe, or just, you can just say any way you want. So someone please try. We will help each other if needed. When should we call something integrable? If we are using general partitions, if you're using any partition. It is just the same thing, just that we have to use general partitions. Yeah. So you want to say that a certain region under the graph of a function has area, and you are going to divide that region using these partitions. Then when should you say that the region has area, has a well-defined legal area? Please try. See, even if you end up saying something which is maybe completely wrong, then that will not be the case, but still, you should say. It is better than not saying. Uh, what do you mean finer than the regular ones? Because so you're saying using general partitions. Okay. Yeah, so that does seem to be the case, but the first thing that you said, that finer than regular partition, see, there is no such thing like that. Because you take any general partition, a regular partition can always fight with it for being fine. I mean, it may not become finer than it, but you see, if you take a general partition, then I can take, I'm not saying that a regular partition will become finer than that, but basically there is no general partition which is finer than a regular partition, than all regular partitions, right? So let's see. Let's say you take this general partition. Dx is there. Dx is sort of there, but see, by general partitions, I mean that the parts don't have to be of equal size. Okay, that is the meaning, general partition. Okay, but if I take a partition like this, or maybe you can say I'll take a very small partition, very small partition. Yeah, this cannot be finer than all regular partitions, right? Because you can always choose a smaller and smaller delta, so that regular partition comes like this. Now, I'm not even saying that the regular partition is finer. Okay, like all the parts of the regular partition are not, that they are not contained in the general partition, right? You can see here, this pink region, this pink region is not contained inside, is not contained in an interval of the red regions. Yeah, it is crossing, but then the red region also is not finer, right? Because the pink region to begin with is smaller. So none of them are finer. Okay, none of them beat the other. Okay, finer means a refinement. You have a partition and you refine it by putting more intervals. None of them are like that here. Okay, so regular partitions, it's not like you can take a general partition and beat all regular partitions. But then what? But what should be the definition here, at least for the integrability? I want to first know that, because unless we have that, maybe we cannot think clearly. Yeah. So let's see. I mean, again, you just want to make the upper sum and lower sum small, right? So for, again, the function and all is same, but for any epsilon greater than 0, there exists a partition, I mean, just a partition P, that is just a general partition, a partition P such that, just simple, it's even more cleaner, but yeah, a lot of things are in it. Does everybody agree? Yeah, it is just the same definition, right? You just want to make the difference between the upper sum and lower sum small, but now you have access to not just regular partitions, but general partitions. Obviously, regular partitions are included, but you have more. Okay, so this is the meaning, the definition of F is Riemann integrable. B. This is with respect to B. B integrable, whatever. Maybe I should say that. Maybe I should say B integrable, and that is A integrable. A integrable and B integrable. You see, these are not the same a priori. Okay, something is integrable here with respect to this definition, which we kind of made up, and with respect to this, they don't look the same. They may not be the same. Can anybody tell me why they may not be the same? Like why there may be a function which is integrable with respect to one definition, but not integrable with respect to the other definition? Let me ask a more specific question. So if f is integrable, if f is a integrable, okay, which means that for any epsilon, you can find a smaller enough delta such that, you can make the upper and lower sum less than epsilon for this f. That's what I'm saying, f is a integrable. If f is a integrable, then does that imply that f is b integrable? We should write integrable. This is not a very difficult question. This is really a test of whether you have understood these things so far. There's no thinking to do beyond that, more or less. Okay, one of you had sent me a good writing thing. I should start using that. Anyway, I should start using one because the Zoom is not very good for writing. Because, yeah, not very good for writing. So you can make the upper lower sum small, small and small as you want using regular partitions. Does it imply that you can do that with general partitions? It's almost like a tautology. So in B, you have access to all partitions. You can use the regular ones also. This, you mean this is true? Yes, so this is certainly true. Okay. Would you or would anyone like to explain? Because it will be more clear, I think. And it should be. Yes, just take the same partition, right? So for any epsilon greater than 0, you used a partition P delta to make the sum, to make the difference less than epsilon. Just use this same delta, right, for that epsilon, because this is also a general partition. This is just the triviality. It's about understanding this thing, just understanding what I've said only. Okay. So is it, Chandan, is it okay with you also? Okay. All right. Okay. Because really, when you want to make the difference small, you can only do that by taking smaller and smaller partitions, right? And when you are able to make, so given an epsilon, let's say the 1/100, you're able to make the difference small using this p delta. But then you can use this p delta in the general partition case also, right? So just making it clear for all of us, because it's a little abstract, that's all. That's the situation with a lot of problems. We don't understand, we don't get comfortable with it early enough to solve it. Anyways, this is simple. But now the question is, does B imply A? That is a real question. So just think. I'll just come in a minute. I have to drink some water. Think. This is a question mark, obviously. Okay. Okay, why does it look true? No, no, no. No, no, no. I didn't. Did I? Okay. If I said that regular partitions can beat general partitions, that is wrong. If I said that, right? So let me write that. Make it clear for all of us. No, that is not correct, because you can also see if I 1 second. Let me just yeah, create more space. So given a general partition, is there a regular partition which is better than that? Okay, which is basically a subdivision of the general partition. If you think that is not correct, right? If I said that, then that is not correct. So you can see what is being asked. So starting with the general, this is just a question of partition. This is not even a question of integration now. Just about this simple thing. Start with a general partition. Okay. But yeah, in the end, we will see something interesting. They don't beat it. Means they don't, you can't refine it. Let's say 0 to 1. If I take a general partition, so I'm taking a general partition, I've written it. It may not be very small. I mean, there's no such thing as small, because you can always take a smaller in terms of size, right? Regular partition. But it's also about number theory. It's also about the multiples. A1, A2, A3. Let's say only 4 terms. Is it necessary that there will be a regular partition which will be a refinement of this? I'll break it down further and further, but first I want to see if you guys can do it like this. You can give me a counter example by choosing some AIs. It's up to you. Or if I'm wrong, then we'll see. L, but if you keep the same L. Yes, and that may not happen, right? So what you are looking for is an L. So first let me say it in the intermediate thing a little bit. So see, basically what are we looking at? We are looking for an L such that there is this L, 2L, and you see some L, like maybe 5L. 5L should become A1. And then some 6L, 7L, but then some L. Yes. No, is it LCM or SCF? HCF, yeah. That's perfectly, that's what it is, right? It's some SCF kind of thing, right? And you're looking for some 100L, right? And then so on. But you see, that may not happen, right? I'm not going to say HCF, but yeah, but SCF kind of thing, but it's not really. Cannot say SCF because these are real numbers. Okay. So do you think such an L can be found for any real numbers, any 4 real numbers? Or even any 2 real numbers if you take arbitrary real numbers, pi and e or something like that? Not right. It doesn't look correct. So that is the problem. Okay, so this may not happen. So you may not be able to find the L. Yeah, you may not be able to find the L. So you can take the L to be anything, but still, it may not happen. Because you can understand, right? Then can just anybody give a quick counter example? I think that will be the best thing. That's much better, right? So you have to just take 2 numbers which are very different, right? So you can maybe take root 2 and root, well, yeah, just forgive the 1, take it 10, root 2 and root 3, whatever. You see, if root 2 is equal to L, if, yeah, root 2 is equal to K1L and root 2 is equal to K2L, root 3, sorry. You see that this is just impossible, right? It just doesn't make sense because yeah, K1 by K2. Remember, K1 and K2 have to be integers. That we have to, okay? So it is not possible. Is a rational. Yes, exactly. Right? Absolutely not possible, right? So it is, so if I said that, so you see the regular refinement, regular partition, you can take a delta to be very, very small, but obviously it doesn't mean that you can use it to refine or use it to subdivide a general partition. Okay. So no matter how small a delta you take, you may not be able to achieve. If we were able to subdivide, then we were done. So let's so the answer here is no, but let's go back and review things a little bit here. You see, f is b integrable. Let's assume this. Okay, so let's say that there is an epsilon greater than 0. Okay, there is a partition, there exists a partition. Let me even write the partition, a1, a2, a3, and so on. Oh, sorry, there is this person on the other side. Yes, bangs the door so much. So you see, I'm just taking a partition such that upper sum minus lower sum is, yeah, I'm not going to write that. That is just here. Okay, I'm just assuming it here. And now we want to just say, is there a delta which can do the same work? Okay, is there a p delta which can do the question? Yeah, question is there a p delta such that, you know, up delta well, let's see. Let's not lose hope. Let's see. I think. Let's see. Okay, so a general partition is doing the job. This is just drawing this to highlight that it is not regular, not necessarily regular. And this is not a continuous function. Okay, otherwise you could do it maybe. Now, can you find a regular partition that can do the job? Now, see, if there was a regular partition which would refine this, if there was a regular partition which would refine, that's why you see I'm drawing the red lines on top of the black ones, then there is no issue, right? If there was a regular, so it's regular, same distance, which would have refined, then there was no problem, right? Because then, since it's going, now this is a refinement of P delta, the upper sum minus lower sum will only decrease. So there will be no problem. But unfortunately, that we cannot do. We have seen. I mean, for a minute, even I was thinking last time, sometime, okay, that it was possible. It's obviously foolish, but yeah, I do think a lot of foolish things. Because in my study of integration, I had never thought about this question. Okay, until last time when I introduced you guys with this regular partition thing, then I was thinking, okay. Then I was trying to think of what to say next, and I was getting a little confused because my my education has been with general. I mean, most of us have learned through general, but I was getting confused. Okay, how because I usually try to make the definitions and stuff on my own. But yeah, obviously I'm using my memory definitely. Then I just open routine and okay, general partition. Oh, everybody uses general partition. So did I make a mistake in the class? For a long time I was thinking I made a mistake, but then I was trying to work it out. I got something interesting. It is a good thing, right? Is there a regular partition that can do the job? No, so you don't want to refine it. So no, you may not be able to refine it. But even then, if you cannot refine it, it doesn't mean you cannot make the integrals, you cannot make the upper and lower sum difference smaller. There may be other ways to do it, right? Obviously, if you can find a refinement, then that's the best way. But if you cannot find a refinement, you could still find a small enough delta which can make this work, even if it's not a refinement. Okay, so that is still there. It is very much there. So you want to be maybe taking a very small delta. and comparing this upper sum minus lower sum of P. So remember we have this. So we have this for this P. Or I might be wrong also. Let's see, we'll see. Certainly you want to be taking a very small delta, but what smallness are we looking at? How small should we take it? So we have a partition P, a general partition, which is making the difference less than epsilon. Now, can it be possible that no matter how small delta you take, the difference is bigger than epsilon for this P delta? While you guys think, let me just expand this, the meaning of this. M1 is the maximum in A1 to A2 to A1. Or maybe I should say between 0 and, so yeah, let's just calling 0 A0. And so on. This is less than epsilon. This is, we are told this. Now try to see if you take a small delta and take the partition, then is it going to be bigger than epsilon, or how would it look like compared to this? How small delta you should take? Just think. So see, first of all, I would certainly like to take delta to be less than all lengths, right? I mean, if I want to have a chance, do you guys agree with that? I mean, if I want to have a chance, I should take my delta. This is what I thought, right? So let delta be minimum of all the lengths of all ai plus 1 minus ai. Just less than them, something less than the minimum. Do you guys agree that this should be my starting point at least? Yeah, because see, if I take delta bigger than that, then at some point what can happen is I will have something like 4 delta here and 5 delta here. Then who's going to save me? Now here, I mean, this will not work, right? Because certainly the maximum in this interval will be bigger than the maximum in the smaller interval A2, A3. And the minimum can actually also be smaller than the minimum in this interval, right? So I'll have a, and that's bad. That's unnecessarily bad. Okay. So to begin with, I want to take my delta to be less than the minimum. Then what could the situation be like? And where will the problems really arise? So you see, just for simplicity, you see, I'm just making something like this, delta here and 2 delta, 3 delta, just for simplicity, and then 4 delta. And this is fine, it's not a loss of generality, 5 delta. Let's say I have a 6 delta. So you want to compare this upper sum, lower sum with respect to this delta partition with the upper sum, lower sum with respect to the general partition. We want to compare these two aspects, these two elements, these two some differences. Okay, so we want to compare this thing and this thing. Because that's our only hope to show, to find a delta which is less than epsilon, right? You want to basically find delta such that this difference between upper sum and lower sum is less than this. That's how you can do, right? Because this that's the only way to compare, right? So the goal is to find a delta so that let me just write it here. It's not a problem. It's a good expression. It's an important expression such that up delta minus epsilon is fixed throughout. Okay, you have to do that for any epsilon. So we start with an arbitrary epsilon. So that is fine. Is less than epsilon. This is the right way to show. This is the right way to find a delta which is less than for which the difference is less than epsilon. Right? I mean, this is the right way to do it. You can't just out of the blue show it, right? You have to compare it with, yeah. And we'll see if we can't find it, then we will kind of realize an obstruction in the end, right? But the only way to realize it maybe is to try to find it because we don't know any theorems here. I mean, I also don't know. So any ideas? Hmm. Mm-hmm. 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 Darbo's integral, I don't get that suddenly. Okay, okay, okay. So you're trying to say, yeah, but do we have such a situation? So we don't completely have the situation, right? So I mean, if we take like these xi's are the ai's, okay, and these are like the some k delta plus one. So yes, from here we get this idea, right? So does everybody see that, for example, you look at this 5 delta and 6 delta. Maybe, Chandan, this is your point, that the area that is, leading from 5 delta to 6 delta, that is a better use of that is going to give us a smaller difference than the one computed by A3 to A4. Right. Even if you restrict the one computed by A3 to A4 in that region. Okay. So does everybody see that? So let me just write that more clearly. Basically, we are seeing that whenever two deltas are inside some AI and AI plus one, then that is a good contribution. The only problem is when the delta jumps, which we have seen number theoretically, we cannot avoid it. But let's make the idea concrete, which is what Chandan is saying, and that will actually do half the problem. So the other half is there. Okay. So yeah. So f of m. So this is a u p. So let's just write this p delta. Okay. This is the difference with respect to p delta. So f of, how should I say? Once again, I'll just say that clearly. Mx fx, right? It's good to say it clearly. To 6 delta, this maximum minus the minimum, or maybe let's just say you guys understand that minus the minimum. Yeah, this is certainly less than f m4 minus f m4. So do all of you agree with this? Okay, you're just taking it on a small interval. This is the idea we have seen several times. Okay, when you're doing it on a smaller interval, it's just like this. Okay, it's seen once a L'Hopital inequality also. Anyways, this thing. Now, this we know that this is a better use, okay, of the interval. So then where is so basically this the p delta difference is winning here. So then where is it losing, and then what should you do? Okay. The problem is that it may lose in this part where the crossings are happening. The problem is happening where, second, problem is happening where the crossings are happening. What can we say about these regions? Yeah, that's why, right? That's why they create a problem. But we have to account for them in the p delta difference, right? In the difference, we have to account for them. So what will happen? We cannot leave them, right? Because they are there. So what do we do with them? That is the problem. Okay. So, right. So then for this, to understand this, let us try to separate So we have this, sorry. If you look at this upper sum, no. So we are going to just separate the good and the bad. Sorry. And this is going to be the lower sum. And then we are going to take the difference. Okay. Now you see, we are going to separate these intervals, k delta, k plus 1 delta. These intervals which are inside some ai to ai plus 1. Okay. We are separating. I'm not writing the thing, but you see there will be some summations there, right? Okay. And then that you can write that. It just gets complicated, but you can write it. Then there is a portion which is outside, which doesn't cross. Okay, so then there is a rest. So then what do? You want to make this difference maybe less than epsilon, or maybe less than this, as I was thinking in the middle. 5 delta and 5 delta and 8. No, we're not going to take 5 delta and 8 delta. 6 delta and 7 delta, right? Or 3 delta and 4 delta. Yeah. Between, yes, yeah, 6 delta and 7 delta, right? It's crossing A4, right? So it is crossing A. Mhm. Uh, mm, yes, I mean, yeah. So I think you're kind of saying that, well, the difference may not be that small, but it won't be too big either, right? Delta is small, and also yes, right? So let's take, for example, this 6 delta to 7 delta, right? So what will be the contribution of this? The contribution of this will be like delta and delta times what? At most, in the worst case, you can take the maximum of, so maybe I'll write that, right? So I'm saying that in the worst case, you can take maximum of the maximum in A3, A4, and A4, A5, right? So you can take max of um, M4 and M5, right? In the worst case. No, the maximum. So maximum can come from M4 or M5. You don't know, right? I mean, yeah. So the maximum, you see, so you have to take the maximum from A3 to A4 and the maximum for A4 to A5. And you have to take the maximum because you're going to take the maximum of the function in this interval, right? So you see, I mean, the maximum between A2 to A4 may occur in this interval, and the maximum from A2, A4 to A5 may also unfortunately occur in this interval, right? Between A4 and 7 delta. And so you have to take the maximum between them if you're unlucky. I mean, if you're lucky, you might get a very small value also, but you have to just take the worst case. Okay. And then you have to also take the difference in that way. Sorry, I mean the minimum in that way. The minimum may also be like that, right? You may end up having, we don't know. I mean, it will be less than this. The contribution will be less than equal to this. This is the worst case. Remember, the n is fixed here. Okay, n is fixed here, remember. Remember, the n is fixed, and Chandan has pointed out that delta can be made smaller and smaller. Delta can be small, right? So the point is that the rest of the thing is delta times something finite. See, it is finite, no doubt, because you're taking a finite n. It has nothing to do with integrability. Do you guys agree with that? I mean, all this analysis is not really important, but it's just that it is finite, but finite times a delta. That's all we need, I think. So are you guys on board? Is it fine? Okay. That is always true because the regular case is contained in the general case. Right? If I've understood you correctly. But that will help you to show that A integrable implies B integrable. If I've understood you correctly. Right. That we have already done. You only told me, right, that it is true. And we kind of also just explain that. That is simple. But this is the real thing. Do you guys agree with this till now? Okay. I suppose Chandan has definitely understood. Rasuvro, you have also understood. Yeah. Yeah. Okay. Yes. I mean, I'm sure all of you have understood, but because this is new, and also I'm a little afraid I might be doing something wrong. So I'm also just confirming. Okay. All right. So now you know that this quantity is less than epsilon, right? It is certainly less than epsilon, right? Because, well, this is less than UP delta minus LP delta. No, I mean, so what I mean is this part only, not this part. Okay, so let me be careful. So this part is less than, so let's call this some t. Okay, so this part is less than epsilon plus, let me not write, don't want to write epsilon, you see. I want to write, I mean, yeah, but you will see why. Either ways you will understand. So this thing plus t delta. Okay, see this part is less than epsilon. Sorry, it's less than UP delta minus LP delta. Okay, because they were contained in those intervals, right? These things were contained in the AIA minus intervals, right? It's going to be strictly less, no doubt. Okay, going to be strictly less. You can also put more in that, how much less and so on. I mean, yeah, you could put a condition, but I don't think we need that in this analysis. So we will not say. Yeah. Yes. So now can you guys finish the problem? So unfortunately, we have not able to show that it is less than UP delta minus LP delta. So I was not correct in that sense. But still, can you guys show that it is less than epsilon? Remember, delta is in your hands. So yeah, can you show that this is less than epsilon? Choose a delta. Certainly true, right? Just take the delta to be small enough. Because I mean, epsilon minus this, epsilon minus, or you can take epsilon by 2 and whatnot, but epsilon minus this, it's equal to something, right? Yeah, so just take delta to be small enough, right? Epsilon 1 by t or something. Then you can do this. And remember that when you change the delta, this t is not going to change. That you have to say, Okay. I mean, the t is only going to decrease. Do you guys see that? That, I mean, as delta goes to 0, t does not increase. Because the first thing is we're not changing the n. And the second thing is that the maximum and minimum, that is not going to increase. That will actually decrease only, or may not decrease, but it will not increase. Okay, it may not increase. Okay, so I suppose this is clear. So this, I think, was a very fine problem. It's not difficult, but there was some analysis in this which was a little good flavor, right? I suppose new flavor a little bit. Not difficult, but yeah, a little bit different. This implies that f is integrable. Yes, yes, that's what I am getting. Yes, that's what we are getting. Yeah, yeah. It's good news, right? It's a good news, right? Not a bad news. Okay, but still, now it means that you can use both of them as you want. Okay, so I mean, the A integrability will help you to find integrals easily, maybe take regular partitions and so on, and yeah, it's enough to consider them. But yeah, I mean, if you can use them, yeah, but no, so B, I don't know, but B can be used to show non-integrability, right? Very easily, because yeah, maybe you could do something. Yeah, yeah, B. I don't know. Yeah, no, B. Yeah, B actually can be used to show integrability more easily because you can use the partition, general partitions to eliminate the bad points. You can put the bad points on the boundary of the intervals, right? On the endpoints and so on. You can think. Okay, you can practice questions of this maybe from Spivak. Spivak calculus integration section has questions of this kind. Language is also very similar. I have not looked at that book for over 7 years, maybe 6 years, maybe. Yeah, long time. But I will also look. You guys can try problems from there. I will do more problems. No, next class will be based on problems. Okay, so today just stopping on very much time because some supposed to stop at 9:30, but yeah. So is it fine? Any questions? If there are any questions, then ask. Okay, then I'm stopping. I hope you guys liked this. This is a certain new thing for me also, which we did today. So yeah.